In the next part of this lecture, we're just going to briefly consider relations in a sort of more general sense than any particular relation for some language, just to build a bit of machinery that we're going to use as we go along in this section. So, as we've seen in some of the previous chapters, we can think of a relation between two values as a prop valued function in this sense. So in this case, this is relating to elements of the x type, but it could be an x and a y or so on. So primarily here we're interested in relations between values of the same type, so we just formalize it like this. So relation of x will be an x to x prop. And in what's coming up, we'll be defining mostly this single step reduction relation. In other words, a relation between programs and programs that are slightly more reduced than that. And also we'll see later on the multi-step version, which essentially is stringing a whole bunch of single steps together. There's lots of other relations, obviously, the examples here show, but the focus in this chapter is on the evaluation relation. So if we have relations that conform to this sort of structure, we can talk about different properties of them. So one that we're going to want in the future is that the small step relation, this arrow, we want it to be deterministic for the imp language, for example. Just like the big step evaluation relation we saw in the previous chapters, it was deterministic. So basically what that will mean is that every time we have a value, in other words, this is a program or a term, when it makes a step, single step to t prime, there's only one possible t prime that could be. We can't sort of fork the evaluation and have a decision about what to do next. There's only one choice for what to do next, is the intention of a deterministic relation. So for the simple language that we've been doing in this chapter with just the plus and the constants, this is the informal argument. So for example, if we've got x stepping, so we have x, we step it to y1 and y2, then we need to show that y1 and y2 must be the same. And so if you think about it, if we step both of them to plus const, right, then there's only one answer for that, right? The uniqueness is determined by the rule for plus const. Now in the cases where the two derivations of the the stepping x steps to y1 and x steps to y2, if they both end with st plus 1 or st plus 2 as the last step, then the induction hypothesis will do that, because we're essentially just talking about the derivation, the stepping of some component, either the left component for st plus 1 or the right component for st plus 2. It can't be the case that we end up with a plus const on one side and a plus 1 or a plus 2 on the other side, because that would imply that for plus const to work, it has to be of the form pt1, t2, where both t1 and t2 are constants. Right? Otherwise, plus const doesn't apply. But for plus 1 and plus 2 to apply, one of the subthings, t1 or t2, has to be a non-constant, has to be a p. And we can't have both of those at the same time, so that combination is ruled out. And similarly, if we have one of them ends with st plus 1 and the other one is st plus 2, they can't coexist either, because the st plus 1 case requires that the left-hand child is a constant, but the st plus 2 case requires that the left child is a constant, and the st plus 1 case requires that it can step, so it has to be a plus. So all those combinations mean that you can never get sort of forking in the evaluation for this particular case. So we can formalize that by saying, well, what does determinism really mean? So this is a definition that applies to any relation over some type x, right? And it's basically saying if x is related to y1 and x is related to y2, then y1 and y2 have to be equal. Right, so this is for any arbitrary relation stating what the deterministic property is. So then this proof here is stating, well, we can show that the step relation, which is the one that formalizes the single step, small step for this simple language, we can prove that it is deterministic in this way. I won't go through all the cases in the proof, but I'll show you a few of them just to give you an idea of how this goes. So you can see here that we've got x going to y1, and the goal now is, well, if there's an x, if there's a y2 such that x goes to y2, then y1 and y2 have to be the same. So the way they do this proof is they do an induction on all the different ways that this step could happen, and that's given by the evaluation rules. And then we have to case out basically. So here, for example, this is the cases where PCC is the thing we're talking about, and it goes to y2, and it's also in the y1 case, it's gone to C n1 n plus n2, right? In other words, this is the case where both of the steps are using the plus const rule. Okay, so if we do inversion on this rule here, we get the constraints that must apply if this step is to exist. So that's going to be that the y2 has to be this sum again. And now we can see in the first goal that both of them are stepping to the same thing. So this is easily solved by reflexivity. And this is the case where one of them is using the plus const rule, which gives us this, and the other one is using the a rule that says we're going to step the left-hand side, right? And in fact, that doesn't really work anyway. So we can see, for example, here, that's a dodgy one. So that's saying that the left-hand side is Cn1 and it steps to T1 prime. So we get this result plus T1 prime Cn2. The problem is that there's no evaluation rule for this step that I've highlighted here. And we should expect that that's the case, because down here we've got a C equals a P. And we know that because C and P are different constructors for this type, they can't ever be equal. So we can get this one by just inversion on H2, because that step can't exist. And this case is very similar as well. So there's another, this is the right-hand child just stepping instead of the left one. That can't happen either. So I'll leave it to you to trace through the rest of these steps on your own just to get an idea. But the more complicated ones use the induction hypothesis to get where they need to go. But the structure is very similar along the bottom here. In the chapter here, there's a little bit of a digression, which I'm not going to go into, which is how to use Cox LTAC meta language to write a new tactic, basically. So there's a bunch of stuff in here that we haven't talked about and won't talk about, to do with matching what the goal looks like, and then trying to apply some things recursive. This is a recursive application of some tactics and so on and so forth. And it basically means by the end down here somewhere, they can do this here with this new tactic, which tries to invert basically anything that it can try to invert, it inverts, and if that actually works to solve the goal, then we're good. So you can see in this simpler form of the proof, all of the cases that were eventually solved by inverting something have been omitted because they're all solved by this new tactic, and the only ones that are left are the ones that actually end up being solved by reflexivity. So don't worry too much about how that works. There's lots of documentation on LTAC if you want to find out, but we won't worry about it here. Okay, so that's relations in general and determinism of the step thing. We'll come back in the next part and start talking about values and strong progress in normal forms.